Well, our next application here is money-weighted returns. We're going to discuss money-weighted returns and time-weighted returns. And the question comes up, why, right? Well, the reason is if a money manager is managing an account and there's cash flows into or out of the account that are not under the control of the manager, then to evaluate the manager's performance in terms of security selection, we want to ignore the effects of those cash flows in and out of the account. So we really want to use the time-weighted returns instead of the money-weighted rate of returns. So let's look at those differences here. For the money-weighted rate of returns, this is an internal rate of return measure. So we're going to look at the cash flows into the account. So the beginning value would be an inflow into the account. And any additions would be positive cash flows. Any withdrawals from the account would be negative. And we're going to calculate the internal rate of return for these. Now, in order to do this, the periods have to be of equal length. So we'd use the shortest period over which there's no significant cash flows, and then try and fit those cash flows to that. For our purposes at level 1, we won't do anything very complex with that, because we need periods of equal length, because when we calculate an internal rate of return, it's for a period. Before, we calculated an annual internal rate of return, but if these periods say quarterly, the firm makes deposits into a pension fund, and quarterly it makes payments out for beneficiaries of the fund, then our IRR would be calculated on these quarterly cash flows, and it would be a quarterly interest rate, a quarterly internal rate of return. So let's work through an example. An investor buys a share of stock at time 0 for 100. The share price at the end of the year is 120. And then the investor buys one more share. Share price at the end of year 2 is 130. And the stock paid a $2 dividend at the end of each year. Calculate the annual money-weighted return. So let's look at what our cash flows are. Initially, we've got a cash flow of $100 into the account. We bought a share of stock. At time 1, our cash flow is $118. Because we bought one more share that cost us $120, but we received a $2 dividend in the account. So all we had to add to the account to buy this second share of stock is $118. So that's our cash flow, a deposit into the account of $118 at time 1. And then we've got our ending value. We've got 2 shares of stock for the second year, and the value at the end is $130 each. So that's $260 there, right? 130 times 2 is $260. But the stock pays $2 a share dividend at the end of the second year, so that's another 4. And so that's the ending value in the account. And we treat that as a cash flow out of the account. So we put that in as a positive number here. It's what we could take out at the end, given these 2 deposits we've made, inflows into the account. And then compute the IRR, 13.86%. Now we've used annual cash flows, so that's an annual internal rate of return. So there it is officially, $120 price minus the $2 dividend. And then we had 2 times 130 plus $4 in dividend. So remember, that internal rate of return makes the present value equal 0, and that's what we're showing there. But it has to be, you have to solve it with your financial calculator. Now for time-weighted returns, we want to take the effect of the cash flows out of there. So all we care about now is the performance, the total return on that stock each period. Now, the general description of an annual time-weighted return is we're going to use this 1 plus the holding period return for each period between cash flows. And then by multiplying those together, we'll get 1 plus the total return if there were no cash flows in or out of the account during those periods, and then take that to the power 1 over the number of years, because we want an annual time-weighted return. And so if we've got 2 years of data here, we've got to take it to the 1/2 power minus 1 to get the annual time-weighted return. But these periods don't have to be equal length. These periods can be any length because we're just compounding them over the entire period. So we're going to calculate these holding period returns for periods between these significant cash flows. So let's go back to our example here and calculate the time-weighted rate of return. An investor buys 1 share for $100 at time 0, and the share price at the end of the year is $120, and the stock paid a $2 dividend. So over that year, we've turned a $100 investment into $122. So our first year holding period return is going to be 22%. Now we'll look at the second period. What's our beginning value of the second period? Well, we've got 2 shares of stock in there, but notice I've calculated it here just for 1 share of stock. And the reason we can do that is it doesn't matter. Your rate of return on a stock is going to be the same, whether you buy 1 share, 10 shares, 17 shares, or 200,000 shares. So here we take that ending value of 130 plus the $2 dividend, so we're getting the total return over the 1-year period. Our beginning value is the value of that share of stock at the beginning of the second year, which was 120. So our return over that second year, our holding period return, is 10%. So multiplying 1 plus that holding period return for the 2 periods, taking to the 1/2 minus 1, we get a compound rate of return of 15.84%, ignoring those cash flows. Now, one thing to think about here is you may be wondering, well, how do those cash flows affect things? Well, notice that our return on this stock the first year was 22%, and the return the second year was 10%. When we looked at the money-weighted rate of return, we had more money in the account the second year. So we're really putting more weight on the second year returns in our money-weighted returns calculation. So by putting more weight on the second year return, which was lower, that means our money-weighted rate of return was less than our time-weighted rate of return. And again, as long as the manager of the account doesn't have control over these cash flows in and out of the account, isn't trying to time the market or anything by going into cash and back out of cash, then we want to ignore the effect of those time flows, because the manager's performance shouldn't be evaluated on the money-weighted rate of return when he or she doesn't have control over those cash flows in and out of the account. Now we've got some definitions here, some yields that you need to learn. BDY, HPY, EAY, MMY. Sounds confusing, doesn't it? Well, a couple of those we've learned. Okay, we learned the holding period yield, and we've got a pretty good idea of the effective annual yield. But we need to take a close look at this bank discount yield and money market yield. The bank discount yield, this is for discount securities. Treasury bills, for example, don't pay explicit interest. One treasury bill we think of as having $1,000 face value, and so it pays that at maturity. And it's sold at something less than that. It's sold at a discount from its face value. And so you buy it at that discounted value, You collect the face value at maturity, and that's your interest right there. And so this is called a bank discount yield. It's not really a yield, but it's an annualized discount from face value. So if this is in currency units, we take the discount over the face value, so that's the percentage discount from face, and annualize it on a simple basis using 360 over the days to maturity. Our holding period yield, we already know, ending value over beginning value minus 1. The effective annual yield is a compounded holding period yield. So we've got 1 plus the holding period yield. Remember, the holding period yield can be for any period. And so that's what we've got here as days. So this is just really how many years we're compounding for. If it's 90 days, we're compounding to a power just over 4, right? 365 over 90. And for the money market yield, we also begin with the holding period yield, and it is a simple annualization, same as we had up here, but it's an annualization not of the discount, but of the holding period yield. Let's put some numbers to this to make it a little clearer. We've got 120 days. That's how many days until maturity at face value. And we've got a T-bill priced at $98,500. Now, a Treasury bill doesn't pay explicit interest. A single Treasury bill has a face value of $1,000. So we're going to buy this for $985, and then 120 days from now, we're going to get paid $1,000. So let's look at each of these yield measures for this Treasury bill. The discount from face value is $15, $1,000 to $985. So we've got 15 over 1,000, that's the discount, 1.5% from face value. And then we annualize that with 360 over the number of days until maturity of 120. So our simple annualized discount, our BDY, or bank discount yield, is 4.5%. The holding period yield we'll calculate just as before. The ending value is 1,000. Our purchase price, the beginning value, is $985. So 1,000 over 985 minus 1, 1.5228%. So that's our 120-day holding period yield. So the effective annual yield, we're going to compound that 120-day rate for the number of 120-day periods in a year. That's our exponent there, 365 over 120. So a little over 3. So that effective annual yield gives us our rate of 4.704. And you can see that's higher than the bank discount yield of 4.5%. That's a discount. This is actually a yield. And our money market yield, we just take the holding period yield and annualize it using that simple annualization of 360 over the number of days to maturity and get a money market yield of 4.57%. We've also got an LOS that has the command word convert in it, and we're asked to convert among these yield measures. The idea here is if we're given two securities and we're given the yields in two different bases, then we need to change one into the other so we can compare those securities and figure out which has the higher yield. So for our example here, we've got a 150-day, $100,000 face value Treasury bill, which we purchased for $98,000. So the discount from face value is 2%. And we're told we got a money market yield of 4.898%. What are the holding period yield and the effective annual yield? Well, we've really broken it down into two steps here. First, we're going to back the holding period yield out of the money market yield. And then we can use that to calculate the effective annual yield. So the first part of that's right here. We've got ending over beginning value minus 1. So there's the holding period yield is 2.041%. Now, we could also look at it this way. we could take that money market yield and we could unannualize it. We annualized it by multiplying the holding period yield, 2.041%, by 360 over 150, that's simple annualization, to get the money market yield. So if we unannualize that, we get back to 2.041. So if we just had the yield and not the price of the T-bill, we could still back that holding period yield out of there. So now we can use that to get our effective annual yield. And again, that's an annualization with compounding for 365 over 150 days, the number of 150-day periods in 1 year. And if we had that effective annual yield and we wanted to go back to the holding period yield, notice the exponent there is just the inverse. So we're going to unannualize that by taking 1 plus that effective annual yield of 5.039% to the power 150 over 365, and we get back our holding period yield. Another term we need to know is the bond equivalent yield. Now it's given in quant here as 2 times the effective semi-annual yield. And this is because bonds, especially in the U.S., usually pay semi-annually. So we've got a 3-month loan. It's got a holding period yield of 2%. So that's our effective 3-month or quarterly yield. And we need to calculate the bond equivalent yield. Well, the first thing we have to do is take this effective quarterly yield and turn it into an effective semi-annual yield. And we're going to do that by just compounding for 1 more period, so 2 3-month periods. So 1.02 squared minus 1, we get an effective semi-annual yield of 4.04%. Now, in our next question here, we've got annual effective yield is 8%. Calculate the bond equivalent yield. Well, I guess we have to double that 4.04 first to get the bond equivalent yield. And now we're going to go the other way around. We're given an annual effective yield of 8%. What's the bond equivalent yield? Well, here we have an effective annual, and we've got to get to an effective semi-annual. So we're going to take 1 plus that annual effective yield. We'll take the square root of that minus 1 and say, well, if we earn 3.923% semi-annually with compounding, that would give us an effective annual yield of 8%. And again, once we have the effective semi-annual yield, we can just double that to get our bond equivalent yield.